This is the beginning of part 4 of our module on market risk management and value at risk, which teaches you to identify price risk for traded positions and to use value at risk, or VAR, to quantify an entity's exposure to a specific risk factor or a portfolio of risk factors that can adversely impact financial performance. We remind you that this part 4 has a single chapter, chapter 6, which contains the final quiz consisting of 10 questions designed to test your understanding of the materials we covered in this module. Question 1. A company buys a 1-year foreign exchange basket call option to hedge its exposure to 3 currencies: Euro dollar, Sterling dollar, and Aussie or Australian dollar, US dollar. The notional amount of each currency is 26 million units of that currency. The basket value at maturity is the US dollar equivalent of the sum of 26 million euros plus 26 million sterling plus 26 million Aussie, using the spot rates against US dollar at expiration. The option payoff at expiration equals the difference between the basket value at maturity and the basket strike of 100 million US dollars if this difference is positive and 0 otherwise. The risk factors for this position include which of the following inputs? Roman 1, the spot rates and the volatilities of each of Euro dollar, Sterling dollar, and Aussie dollar. Roman 2, the 12-month interest rates in US dollar, Euro, Sterling, and Aussie. Roman 3, the deltas and gammas of the option with respect to each of the FX spot rates. Roman 4, the correlation coefficients between Euro dollar, Sterling dollar, and Aussie dollar. Here are the 4 permissible answers. Solution to question 1. Risk factors for a position are defined as the market variables whose changes directly affect the value of the position. As with any FX option, FX spot rates, their volatility, and the interest rate for the term and base currency are certainly risk factors. Here, our underlying is a basket of currencies whose volatility is determined by the volatility of each individual FX rate and also by the correlation of the spot rates with each other. Delta measures linear sensitivity for an option to spot rate changes, while gamma is a convexity measure that captures the nonlinear relationship between the option value and the changes in spot rates. So delta and gamma are sensitivity measures, not risk factors. Therefore, the answer is C. Question 2. Consider a position with 2 risk factors, F1 and F2. VAR1 and VAR2 are the position's respective one-day value at risk at a 99% confidence level using the variance-covariance method. If var1 equals $4 million and var2 equals $9 million, and assuming the same confidence level and that a week has 5 trading days, the respective aggregated weekly VARs using correlation coefficients for weekly percentage changes in F1 and F2 of alternatively minus 100%, 0, and 100% would be, here are the 4 permissible answers. Solution to question 2. First, we need to convert the one-day VARs into weekly VARs. Since we are applying the variance-covariance method, we simply use the square root of time relationship, whereby weekly VAR equals daily VAR times the square root of 5. So the weekly VAR 1 is 4 million times the square root of 5, which comes to $8.9 million, and weekly VAR 2 is 9 million times the square root of 5, which comes to 20.1 million. Next, we apply the formula from chapter 3 for the diversified VAR of a position with n risk factors. Remember this ugly formula here, where var I is the individual VAR relating to risk factor I, and rho ij is the correlation between the percentage changes of risk factors I and j. In our present case, n equals 2, so our equation above becomes this. Applying now this formula with rho 1, 2 equal alternately to minus 100%, 0, and plus 100% reveals the following results. Therefore, the correct answer is C. Question 3. A U.S. bank has the following 3 FX positions: long 20 million euros, long 20 million Canadian dollars, and short 3 billion Japanese yen. Current market data appears next, including spot levels, volatilities, and correlations. Using the variance-covariance method at a 99% confidence level, the undiversified and diversified aggregated FX VARs over one day are, here are the 4 permissible answers. Worksheet Q3 solution lays out the solution based on our earlier discussion from Chapter 3. In the first table here, we reproduce the inputs from the question. In the second table, we list first the risk factors, which are the 3 spot rates: Euro-dollar, dollar Canadian, and dollar yen. The fair values of these positions appear in cells C10 to E10. Note that for euro, the notional is multiplied by the spot rate as it is quoted as the base currency against the dollar, while for Canadian and for yen, the notional is divided by the spot as they are quoted as term currencies against the dollar. In cells C11 to E11, we apply standardized shifts to the risk factors, remembering that these shifts have to adversely affect the position value. The bank is long 20 million Canadian dollars, and since the Canadian dollar is quoted as the term currency against US dollar, a positive 1% shift would have an adverse impact on the position. The bank is also short 3 billion yen, which is also quoted as the term currency against dollar. So a negative 1% shift would have an adverse impact on the position. We derive the new euro-dollar, dollar-Canadian, and dollar-yen spot rates in cells C12 to E12. We revalue our positions in cells C13 to E13, and we calculate the position value sensitivities to adverse shifts in the relevant risk factors in cells C14 to E14. In the third table, starting here, we convert the annual vols into daily vols in cells C16 to E16. Recalling the square root relationship, we set daily vol equal to annual vol divided by the square root of 260. Given the normal distribution assumption under the variance-covariance approach, the worst adverse potential movement at a 99% confidence level corresponds, you should remember, to either minus 2.33 sigma or plus 2.33 sigma, depending on the sign of the shift in the risk factors in cells C11 to E11. Therefore, we use plus 2.33 sigma in cell D17 and minus 2.33 sigma both in cells C17 and E17. We convert these adverse moves into multiples of unit shifts in cells C18 to E18 through simple division. Finally, the individual VARs in cells C19 to E19 are calculated as the worst adverse potential movements expressed in multiples of unit shifts multiplied by the absolute value of the position sensitivity to shifts in risk factors. The undiversified VAR is calculated in cell C20 as simply the sum of individual VARs, revealing an answer of 1,352,413. The correlation matrix for the percentage daily changes in risk factors is next reproduced in cells B22 to E25. For diversified VAR, as explained in Chapter 3, we first calculate each line of the formula at a time using the sum product function, with the results appearing in cells C27 to E27, in accordance with what we did previously. The diversified VAR is set equal to the square root of the sum of cells C27 to E27 in accordance with the formula, revealing an answer of $690,459. Therefore, the correct answer is B, as in boy. Question 4. A U.S. bank shorts a 2-year UK government zero-coupon bond having a face value of 125 million sterling. The current UK government 2-year zero-coupon rate is 6.6% annually compounded using a 30-360 day count convention, which is equivalent to a price of 110 million sterling for the 2-year zero. The bank also purchases a 2-year European sterling call US dollar put on 110 million sterling, struck at the current sterling dollar spot rate of 1.6, when the 2-year zero coupon rate in US dollars is 4% and the 2-year volatility for sterling dollar is 15%. The risk factors for this aggregate position are, and here are the 4 permissible answers. Solution to question 4. We remind you again that risk factors are those market variables whose changes directly affect the value of the position. For the UK government bond, the first risk factor for the bond position is the 2-year zero coupon rate for GBP. Since the bank is based in the US, while the bond is denominated in sterling, the bond position is also impacted by changes in sterling dollar spot, which is therefore the second risk factor for the bond position. For the FX option position, risk factors include sterling dollar spot, sterling dollar vol, and the 2-year zero coupon rates for dollars and sterling. Again, delta, gamma, duration, convexity are sensitivity measures rather than risk factors. Therefore, the correct answer is B, as in boy. Question 5. Using the inputs from question 4 and applying the analytical method to calculate individual sensitivity measures, the aggregate position sensitivity to a positive 1% movement in sterling dollar spot and a negative 1 basis point movement in the 2-year zero coupon rate for sterling are, here are the 4 permissible answers. Solution to question 5. To calculate the aggregate position sensitivity to the movements indicated in the question, we follow these steps. First, we calculate the linear sensitivities to the sterling dollar spot rate and the 2-year zero coupon rate using the analytical formulas for duration and delta. Second, we calculate the convexity factors under the option for sterling dollar spot and under the bond for the 2-year zero coupon rate. Third, we aggregate the bond and option sensitivities to these two risk factors to derive the aggregate position sensitivity. To achieve this task, we use two worksheets we already developed in this module, RS FX option and RS bond numerical. Worksheet Q5 Solution 1 adapts our old worksheet RS FX option to our present case by first changing the inputs in cells C4 to C9 and then applying the positive 1% shift in the sterling dollar spot and the negative 1 basis point shift in the 2-year sterling zero coupon rate. The linear sensitivity and convexity factor are shown in cells C16 and C17 for the sterling dollar spot, while the linear sensitivity to the sterling 2-year zero coupon rate is shown in cell D16. Similarly, worksheet Q5 Solution 2 adapts our old worksheet RS bond numerical to our present case by first changing inputs in cells C4 to C8. This time we have added in cells C11 to C16 the sterling dollar spot sensitivities that are analogous to any spot position where we are short a currency against the US dollar. We have also applied the positive 1% shift in sterling dollar spot and the negative 1 basis point shift in the sterling 2-year zero coupon rate. The linear sensitivity and convexity factor are shown for the sterling 2-year zero coupon rate in cells D16 and D17, while the linear sensitivity to sterling dollar spot is shown in cell C16. Finally, in cell C18, we calculate the aggregate position sensitivity to sterling dollar spot as the sum of the linear sensitivity from the bond position plus both the linear sensitivity and convexity effect from the option position. This leads to a total sensitivity of negative $1,059,761 in respect of a positive 1% shift in sterling dollar spot. We do the same for the 2-year sterling zero coupon rate in this cell D18, where the aggregate position sensitivity is the sum of the linear sensitivity from the option position plus both the linear sensitivity and convexity effect from the bond position. This leads to a total sensitivity of negative $6,923 in respect of a negative 1 basis point movement in the 2-year sterling zero coupon rate. Therefore, the correct answer is A, as in apple. Question 6. A company buys for $406,844 a euro 10 million best of rates euro call US dollar put expiring in 4 months and paying at maturity per euro of notional amount. This expression here, where S followed by a number of months is the euro-dollar spot rate observed that number of months after today. The current euro-dollar spot is 1.4. The 4-month dollar and euro interest rates are 3% and 5% respectively, and euro-dollar 4-month vol is 10%. Since this option is path dependent and no closed form formula exists for its valuation, we will use Monte Carlo simulation as illustrated in worksheet MC VAR average option, but adapted to the payoff formula for this option, and we will apply the same standardized normal random values that were in cells C22 to F1021. The estimated 99% daily VAR specific to movements in euro-dollar spot is, here are the 4 permissible answers. Detailed steps for the simulation appear in this worksheet Q6 solution, with the initial data in cells C4 to C9. Note the 4-month tenor in cell C8. We first calculate in cell C13 the spot level that would result from a potential 1-day adverse move at a 99% confidence level, and find an answer of 1.3798. From this new level, we now simulate future euro-dollar spot rates for the next 4 months in intervals of 1 month each, as reflected in cell C16. As required, we use the same random values as in the original worksheet by copying those into cells C22 to F1021. The future spot rates for euro-dollar are generated via the same equation we used in worksheet MC VAR average option, with mu equal to 2%, sigma 10%, and delta t this time 0.08. The 1 month euro-dollar spot is generated in cells G22 to G1021, starting as before with spot at 1.4 3798 and applying the stochastic formula as in the earlier worksheet. The 2-month rate is generated in cells H22 to H1021, with each value once again starting from the 1-month simulated spot rate in the cell immediately to its left, and applying to it once again the stochastic formula. The same procedure is repeated for the 3-month and 4-month spot rates in cells I22 to J1021. We next calculate in cell K24 the present value of the option payoffs at maturity all the way up and down this column K, using, as before, the generated spot rates and the options payoff formula shown earlier. As before, the option value in cell K1022 is simply the average of those PVs. And finally, the 99% VAR in cell C18 is equal to the absolute value of the difference between the new and old position values, which equals $129,746. Therefore, the correct answer is A, as in apple. Question 7. A U.S. bank has the following FX positions: long 30 million euros, long 30 million Canadian dollars, and short 4 billion Japanese yen. The current spot levels are as shown here. Based on the daily historical data in worksheet question 7, which you will need to open to answer this question, and specifically in cells B20 to E520, the 99% one-day aggregated VAR is, here are the 4 permissible answers. We begin on this worksheet Q7 solution by calculating the position sensitivity to an adverse 1% change in the relevant risk factors, namely the euro-dollar, dollar-Canadian, and dollar-yen spot rates. The position sensitivities to unit shifts appear in these cells C15 to E15. The next step is to calculate the daily percentage changes in euro-dollar, dollar-Canadian, and dollar-yen, and revalue the change in the aggregated position after applying these daily percentages. We do this towards the bottom in columns F, G, H, I. All exactly as before. The 99% one-day aggregated historical VAR is next calculated in cell C16 as simply the first percentile of the values that were calculated in I-20 to I-519, revealing an answer of $1,654,233. Therefore, the correct answer is A. Question 8. Best Bank holds the following bond portfolio. Best Bank also has the following interest rate swap positions. Under the BIS standardized approach, the aggregate market risk capital charge to the nearest thousand related to these positions is, here are the four permissible answers. In this worksheet, Q8 solution, which is modeled after our earlier worksheet BIS fixed income, we first slot the bonds and derivatives into the appropriate time bands, including, of course, the issuer type and the position size. As explained in Chapter 5, pay-fixed swaps are deconstructed into a U.S. government long FRN with a tenor equal to the next reset date and a short U.S. government fixed rate bond maturing on the same date as the swap. We next draw your attention to cells F7, F15, and F18, in which we add together the notional of bonds and swaps, as the issuer is considered to be the government in both cases. We now apply the specific risk weight stipulated under the standardized model in cells G6 to G21, and from them derive the specific charges for capital in cells H6 to H21. The general market risk charges are also calculated in cells J6 to J21, in each case by multiplying, for example, as we do here, the position size by the appropriate risk weight stipulated under the standardized model. The vertical disallowances within time bands are calculated in cells C28 to J29. The only offsets between long and short positions within time bands are in rows 9 and 10 and rows 13 and 14. Horizontal disallowances within time bands are calculated in these cells here, C31 to J49. The only offset here is in zone 3, between a long position in the 7 to 10 year time band and a short position in the 4 to 5 year time band. The resulting capital charge is calculated in cell J49, right here. There are no horizontal disallowances between time bands, since all residuals in these cells G36, G41, and G49 are positive, meaning there is nothing left to offset, only to aggregate. Finally, the aggregate capital charge appears in cell J60 as the sum of the previously calculated charges, namely $1,209,000. Therefore, the correct answer is D, as in David. Question 9. The commodities desk at Best Bank is actively trading aluminum on the London Metals Exchange. The desk holds the following futures contracts. If the current spot price for aluminum is $2,100 per ton in dollars, then under the BIS standardized model for market risk, the capital charge related to these commodity positions is, here are the 4 permissible answers. In this worksheet Q9 solution, which is modeled after our earlier worksheet BIS commodity, we first convert the size of each position into US dollar values using the current aluminum spot price of $2,100 per ton. We slot amounts into the appropriate time bands in cells C17 to D23, depending on the contract maturity and the direction, i.e., long or short. As explained in Chapter 5, matched positions are reported in cells H17 to H23, to which we apply a capital charge of twice the 1.5% spread rate mandated under the standardized model, as shown in these cells here, J17 to J23. Amounts carried forward for eventual offsets are calculated in these cells I17 to I23, and their related capital surcharge is calculated in cells K17 to K22. Note carefully. We apply a final capital charge of 15% to the last amount carried forward into the more than 3-year time band here in K23. The aggregate capital charge is calculated in cell K24, revealing a value of $5,443,200. Therefore, the correct answer is C. Question 10. A bank is short a 12-month European call option on a commodity struck at 490 when spot is 500. The 12-month risk-free interest rate is 8% per annum, and 12-month vol is 20%. The option's premium is 65.54. The options delta and gamma have been calculated to be as shown here. The options vega defined specifically to mean the change in price corresponding to a positive 1% change in implied volatility is 168. Calculate under the delta plus method of the BIS standardized model the position's capital charge for the delta, gamma, and vega risks, assuming that the bank has no other positions in the trading book. Here are the 4 permissible answers. Solution to question 10. Step 1 under the delta plus method is to multiply the options delta by the market value of the underlying commodity. Thus 500 times 0.721 equals 360.5. This is our delta equivalent. This delta equivalent position is then incorporated into the maturity ladder. And since no other positions exist, the delta equivalent position is multiplied by 15% to generate a capital charge for delta equal to 54.075 as shown here. For gamma risk, the capital charge is calculated pursuant to the formula provided in Chapter 5, namely that the gamma impact is half the gamma times VU squared, where VU, in this case, a commodity, is 15% times the market value of the commodity. So the gamma impact turns out to be 9.5625. Finally, for the vega risk, we are required to simulate an adverse movement in vol of 25% from its current level, which in this case means a 25% relative increase from the current 20%, i.e. by 5 absolute percentage points. Since the current vega is 168, we remind you, then a 1% increase in vega would result in a mark-to-market loss for the bank of 1.68, and therefore a 5% increase would result in a mark-to-market loss, hence the vega impact, equal to 8.4. Therefore, the correct answer is B as in boy.